Hello everyone, welcome back to another physics video. I'm Physics Michael, and in today's lesson, we're going to explore the different types of waves. Waves are all around us, from the light we see to the sound we hear. So it's really important to understand their types and properties. Today, we will look at the differences between frequency waves and stationary waves, transverse waves and longitudinal waves, mechanic waves and electromagnetic waves. Then we'll explore the electromagnetic spectrum. Let's get started. First, let's talk about frequency waves and stationary waves. A frequency wave is a wave that transfers energy from one point to another without moving any matter, just like the wave on the string shown in the animation. The wave pattern moves to the right, and energy is transferred along the string. In contrast, a stationary wave does not transfer energy. As shown in the animation, the pattern of the stationary wave simply oscillates up and down without traveling along the string. So energy stays in place and is not transferred. Next, let's compare transverse and longitudinal waves. In the transverse waves, the oscillations are perpendicular to the direction the wave travels. In the animation, the absorbed particles move up and down while the wave travels left to right. So that's a transverse wave. Light and water waves are typical examples of transverse waves. On the other hand, in a longitudinal wave, the oscillations are parallel to the direction of wave travel. That means the particles move back and forth in the same direction that the wave is moving. In the animation, the particles vibrate left and right, which is the same direction the wave travels. A sound wave is a typical example of a longitudinal wave. Air molecules vibrate back and forth along the direction that sound moves. Now let's look at the difference between mechanic waves and electromagnetic waves. Mechanic waves need a medium to travel through. That means they cannot move through a vacuum. This is because mechanic waves rely on the vibration of particles. For example, water waves depend on vibrating water molecules. Sound waves in air depend on vibrating air molecules. Waves on a string depend on the vibration of the string's particles. These are all mechanic waves. In contrast, electromagnetic waves do not need a medium. They can travel through empty space or a vacuum. That's because electromagnetic waves are oscillations of electric and magnetic fields moving through space. They don't need any particles to carry them. In the picture, you can see that the electric and magnetic fields oscillate perpendicularly to each other and to the direction the wave is traveling. So electromagnetic waves are also transverse waves. Now, let's talk about the electromagnetic spectrum, a family of electromagnetic waves that includes gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwaves, and radio waves. These waves all differ in their wavelengths. Let's begin with the part we know best, visible light. This is the portion of the spectrum we can see with our human eyes. Visible light has wavelengths that range from 400 nanometers to 700 nanometers. That's the same as 4 times 10 to the power of negative 7 meters to 7 times 10 to the power of negative 7 meters. If the wavelength is greater than this, from 7 times 10 to the power of negative 7 meters up to 1,000th of a meter, it is in the infrared region. Microwaves range from 1,000th of a meter to 1/10th of a meter, and radio waves have wavelengths greater than 1/10th of a meter. On the other side of the visible light, where the wavelengths are shorter, from 10 to the power of negative 8 meters to 7 times 10 to the power of negative 7 meters, we find ultraviolet rays. X-rays have wavelengths from 10 to the power of negative 13 meters to 10 to the power of negative 8 meters. And gamma rays range from 10 to the power of negative 16 meters to 10 to the power of negative 10 meters. As you can see, X-rays and gamma rays overlap in their wavelength ranges. Even though these waves have different wavelengths, they will travel at the same speed in a vacuum. This is known as the speed of light, which is about 3.0 times 10 to the power of 8 meters per second. We can use the wave speed formula to calculate the frequency. The formula is wave speed equals frequency times wavelength. For example, if a beam of light travels in a vacuum and has a wavelength of 600 nanometers, what is its frequency? We use formula frequency equals speed divided by wavelength. Substitute the values. Speed is 3.0 times 10 to the power of 8 meters per second. Wavelength is 600 nanometers, which is 6 times 10 to the power of negative 7 meters. So the frequency is 5.0 times 10 to the power of 14 Hz. Now let's try identifying the types of some waves. Water waves are mechanical and transverse because they rely on water particle vibration and the oscillation is perpendicular to the wave direction. Sound waves are also mechanical, but they are longitudinal, since particles vibrate along the same direction sound travels. Visible light is a part of the electromagnetic spectrum, so it is an electromagnetic wave and a transverse wave. Next, let's calculate the wavelengths of some electromagnetic waves using the wave speed formula. After doing the math, we found wave A has a wavelength of 3 times 10 to the power of negative 2 meters, so it is a microwave. Wave B has a wavelength of 5 times 10 to the power of negative 7 meters, which means it is visible light. Wave C has a wavelength of 6 meters, so it belongs to radio waves. Wave D has a wavelength of 5 times 10 to the power of negative 15 meters, which is in the gamma ray range. Wave E has a wavelength of 1 times 10 to the power of negative 5 meters, so it's in the infrared range. Now let's summarize today's lesson. Frequency waves transfer energy from one point to another, while stationary waves do not. In transverse waves, oscillations are perpendicular to the wave's direction. In longitudinal waves, oscillations are parallel to the wave's direction. Mechanic waves cannot travel through a vacuum. Electromagnetic waves can. The electromagnetic spectrum includes gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. These waves differ in wavelengths, but travel at the same speed in vacuum. That's all for today's video. Thanks for watching. I hope you now have a better understanding of how to identify different types of waves and how the electromagnetic spectrum is organized. I'm Physics Michael, and I'll see you in the next video.